Hi all. In today's class, we'll be discussing about model analysis, different types of similarities, forces acting on a flowing fluid, and introduce you to dimensionless numbers. So before I go into your model analysis, you should understand what is the difference between a model and a prototype. A model is a small version of your actual structure, whereas your prototype is your actual structure or just before the actual structure. Now, when I deal with a hydraulic structure or a hydraulic machine, remember these are huge structures, both your hydraulic structure like a dam or a weir or a barrage and a hydraulic machine like your turbine. These are huge investment structures. So before I actually go for the construction for it, I need to know how does it perform. So what do? I make a model. A model is a miniature version of the actual structure or machine, and then I'll be doing studies on that. Okay, for example, I'm taking the turbine. I'm making, I'll take the example of a Pelton wheel turbine. The same setup I'm making in a smaller version, making water to pass, see what is the efficiency for different heads for different discharge, and then I'll this my design, change my design or change some of the measurements and all to see where does it work best. And once I fix the design, I will scale it up to a prototype. Okay, so since your structure and turbines, your structure and your machines are dealing with huge investment and huge lot of people are involved, it is necessary that a model is constructed, a model is studied well to know what are the effects, side effects, everything, and then it is actually implemented. So coming back, a model is a small replica. The prototype is the actual structure of machine. I won't say it's the actual structure, just before the actual structure. A prototype has functionalities, almost the same functionalities, but it is still under consideration. Okay, it is not yet fully developed. The prototype is made, and then you are improving the functionalities once it's constructed. Now once it's all set, then you call it as an actual machine or your structure. Till then, when the studies are still going on, though it is the same size of the actual structure, it is called as a prototype. So in prototype, again, you can have different variations. And finally, if the structure is prototype is ready, then only my actual structure, it is called as my actual structure. Okay, and the study of these models are called as model analysis. Now, what are the advantages? Now, we had dealt with dimensional analysis, model analysis. So, your dimensional analysis, we had told that we are trying, based on the dimensions, we are trying to find the relationship between your independent variable and the new dependent variable. And model analysis, we are doing studies on a small model, and then knowing the model well, how it is performing, I'm scaling up to the prototype. So, some of the advantages are you can predict the performance. Okay, if I don't have a model, I just don't know how does it perform. It's just a trial and error. Like it can be a eureka, oh, it is performing this bad or good. But if I have a model study, I can know, at least predict it in a good way, that okay, how it is going to perform. Now, with the help of your dimension analysis, you're already getting the relationship, relationship between the different variables. So this relationship will help me in conducting my model test. So I'll be knowing, okay, if I have an, Pelton wheel, if the diameter is more, the performance can be better. If the head is more, the performance can be better. So I can have, based on my dimension analysis, I can have a relationship, and I can use this relationship in model testing for understanding your machine or your structure better. Since we'll be making different models, I can select the best model and then scale it up. Okay, again, since models are not as costly as my actual structure, I can vary my design, see which is working best, and then scale it up. Now, when I'm saying model, it is all working model. Okay, it is not just a model, replicate this. It is all working model. Now, the test performance models, okay, helps in getting useful information about the prototype. See, we be having something in our mind, but we don't know the full performance of it. So if you do a number of model studies, we can very well say, okay, this is how the prototype is going to behave, and give a lot of information of, how is the prototype going to behave. So these are some of the advantage of your dimensional and model analysis. Now next, coming to similitude. Similitude is basically similarity. There should be similarity between the model and its prototype. Okay, so we have a model. When I prototype it, when I make into a scale up to it, it should have relationship between your model and prototype. There are three types of similarity: geometric similarity, kinematic similarity, dynamic similarity. So geometric is all about your dimensions. Kinematic deals with your velocity and acceleration, as in kinematics. Your dynamic deals with your forces. So these are relationship which has to be maintained between the model and the prototype. So coming to your geometric similarity, when the ratios of the linear dimensions in the model and prototype are equal, it is said to be geometrically similar. Okay, I think the word itself very clearly says geometric similarity. Your dimensions should be similar. Your linear dimension should be similar. Okay, I'm not saying equal. It should, when I say similar, it should have a ratio. So coming to it, I'm taking a cuboid length example. I'm just taking this example. I have the model, length of the model, breadth of the model, height of the model. Similarly, the prototype, I have the length, your breadth, and your height. And knowing the length and width, I'm calculating the area of the model. Similarly, area of the prototype. Knowing the length, width, and height, I'm calculating the volume of the model, volume of the prototype. Now, for geometric similarity, if I'm saying it is geometrically similar, the proportion, the ratio of length of prototype by length of your model should be equal to your breadth of prototype by breadth of model, should be equal to your height of prototype by height of model, and all should be a ratio. We call that as LR, that is your scale ratio. So each dimension should be having a ratio. Okay, I can't have L by P by M, L by M is equal to 1 ratio. This different ratio, all should have the same ratio. Sometimes even diameter comes in. The diameter also is your dimension. And for area, again, so this is the main relationship for geometric similarity. I can even interpret that for area. So area of prototype by area of your model. Your area is length into breadth, length into breadth. So this is your LR, LP by LM. This is also your LR. So that should be equal to LR square. So your proportionality should be AP by AM should be is equal to LR square. Okay, where LR is your scale ratio. So if I consider the volume, again, all these are having a ratio. So it should be equal to LR cube. So this is your geometric similarity. Now coming next to kinematic similarity. So here the ratios of the velocity and acceleration at the corresponding points. See, in dimensions, we didn't have, in geometric, we didn't have the points. Here at the corresponding points in the model and corresponding points in the prototype are same. Now when I say corresponding point, my first point, now I'm having a hydraulic machine. It has got a set of, hydraulic machine. I'm considering a turbine. A turbine has an inlet pipe, outlet pipe. So I am considering the pipe, inlet pipe. Okay. The point where my pressure is measured, for example. So that same point in my prototype, the same point in the model should be considered. I can't have two different places. Where is my pressure being taken at model, the pressure being taken at your prototype? The same point has to be considered in the model as well as your prototype. The other example I give is if I'm modeling a expansion joint. Okay, so at the model, if I'm taking your expansion joint is increasing area, from your start of increasing area, even in the prototype, that point should be from the start of increasing area. So what you're measuring, either the velocity or your acceleration. So corresponding point is very important. And here both direction of the vector quantities also should be same. If I'm dealing with velocity, the velocity should have the same direction. Acceleration, it should have the same direction. Now here I've taken in the fluid, let Vm1 velocity at 0.1 in model, Vp1 velocity at 0.1 in prototype. Okay, only the scales are different, the point will be the same. As I mentioned, expansion, start of expansion, start of expansion. M2 velocity at 0.2 in model, velocity at velocity of prototype at 0.2. Acceleration AM1 acceleration at point 1 in model, AP1 acceleration at point 1 in prototype, AM2 acceleration at point 2 in model, AP2 acceleration at point 2 in prototype. So we are dealing with model and prototype. So for kinematic similarity, if I'm dealing with velocity, the velocity of prototype at point 1 by the velocity of model at point 1 should be equal to the ratio of velocity of prototype at point 2 divided by velocity of model at point 2, and that should be equal to a ratio called as VR, which is the velocity ratio. Okay, so for kinetic similarity, this relationship has to be should be followed. Now coming to acceleration, again the same thing. Acceleration of prototype at 1, acceleration of model at 1 should be equal to the ratio of acceleration of prototype at 2 divided by acceleration of model at 2, and the ratio is called as acceleration ratio. So this is your kinematic similarity. Now next, coming to your dynamic similarity. So here we are dealing with forces. So when the ratio of the forces acting at the corresponding point. So here also your corresponding point is important. So when I'm considering forces, the forces are different. There are different types of forces. So we are considering the force at a particular point and we are finding the ratio in the model and the prototype. Then it is said to have your dynamic similarity. Here also the direction of the forces should be same. So I'll introduce 2-3 force terms. Inertial force. So FIM is inertial force in model. FIP is inertial force in prototype. I'm defining viscous force in model and prototype. Gravity force in model and prototype. So for dynamic similarity, my inertial force of prototype by inertial force in model should be equal to the ratio of viscous force in prototype, viscous force in model, should be equal to your gravity force in prototype divided by gravity force in model, and that should be equal to your force ratio. So different forces, but the ratios again should be same. And all these are taken at a particular point, not at different points. At the same point, all these forces ratio is being taken. So between the model and the prototype, these 3 similarities should be followed. Only then, if I scale up to a prototype, does it work according to what was expected. Now next, coming to the types of forces in a moving fluid. Now remember types, we'll be dealing with 6 types of forces. Remember, all are not dominant. Like I'll give you an example. If you have a running race where 6 people are supposed to run, there will be 1-2 people who are the top. Remaining people are running, but they're not very dominant. So similarly, in your flow, they based on your pipe flow, gravity flow, there are certain forces which are very dominant, which is important. The other forces are there, but it is insignificant. Though all the forces are acting, like I told you in a running race, everyone are participating, but 1-2 people will be in the lead. Similarly, which they will be dominating it. So similarly here also, 2-3 forces are always dominant, which they are more prevalent than the other forces, depending on the cases being considered. Okay, whether it's pipe flow, open channel flow, whether it's an expansion, okay, whenever the fluid is very viscous. So depending on that, the forces are considered. Now first is the initial force. Inertial force itself is your resistance due to your mass. The formula is equal to mass into acceleration, but in the opposite direction of acceleration. It is a resistive force due to your mass of any structure or machine. So it is equal to product of mass and acceleration and acts in the opposite direction. So if I calculate my inertial force, Fi is m into a. Mass is generally represented as rho into volume. Acceleration, I'm writing it as velocity divided by time. So I'm moving the time to volume, under volume. So I'm shifting from velocity, I'm putting under time. Volume I'm writing as area into length, length by time, and here into velocity. So here rho area, your length by time is velocity into velocity. So I'll be getting my inertial force finally is rho a v square. Okay. So this is my inertial force. The second is my viscous force. So it is equal to the product of shear stress due to viscosity and surface area of flow A. So it's considered in problems where viscosity is significant. So your shear stress is based on your Newton's law of viscosity. Tau is equal to mu du by dy. So I'll substitute it here in tau. mu du by dy into A. Your du is your change in velocity. I can replace it with velocity. Dy is a length. I'm writing in terms of L. So mu V by L into A is your viscous force. Coming next to gravity force, your gravity force is considered an open channel. Remember, the flow is mainly happening due to your gravity. So here it is equal to product of mass and acceleration due to gravity. So I have got m into g, mass again rho into volume into g. Volume I'm writing is area into length. So rho al, g is my gravity force. Next force is your pressure force. It is mainly considered in your pipe flow. It is equal to the pressure intensity P and cross-sectional area A. So here Fp is equal to P into A, P, A. Next is your surface tension force. Your surface tension mainly comes in your droplets, water, drops and thin films. Okay. So it is equal to the product of surface tension and length of surface of flow, L. Okay. So Fs is equal to sigma into L. Surface tension is represented as sigma, sigma into L. And the last force is your elastic force. So it is equal to the product of elastic stress K and area of flowing fluid A. And it is given by K into A. Okay. So these are the different forces considered in a moving fluid. As I told you, certain forces are more dominant compared to others. Though all the forces are there, when I consider a problem, certain forces are more dominant. Now next, I've summarized all the types of forces: inertial force, viscous force, gravity force, pressure force, surface tension force, and elastic force. Now next I'm going to define dimensionless number. Okay, so that's why I gave a recap of all the forces. In all the dimensional number, your numerator is your inertial force. Your denominator will be your viscous, gravity, pressure, surface tension, and elastic. So coming to your dimensionless number. So first number is your Reynolds number. It's a ratio of inertial force by viscous force. Reynolds number. The second is my Froude's number. It is a ratio of root of inertial force divided by gravity force. So here under root is there. Inertial force by gravity force. The next is my Euler's number. It is the ratio of root of inertial force by pressure force. Next is Weber's number. Your Weber's number is root of inertial force by surface tension force. And the last one is Mach's number. It is a ratio of root of inertial force by elastic force. So everywhere the numerator is inertial force. Inertial force is a resistance offered by the mass divided by the different forces which is acting. So Reynolds number, the denominator is viscous. Froude's number, it's gravity. Euler's number, it is pressure. Weber's number, it is surface tension. Mach's number, it is elastic. Only for Reynolds number, you don't have under root. Remaining all have got under root. And see this names also, because in the next slide, I'm simplifying the equation. So your Reynolds number is a ratio. So your inertial force is rho AB square divided by mu V by L into A. My A will get cancelled. My L is going on top. So your Reynolds number is rho VL by mu. So in pipe flow, your L is replaced by your diameter. Okay. Now your Froude's number is, again, initial force is rho AV square divided by rho ALG. So A will get cancelled, rho also gets cancelled, V square by LG. So I'll have V by root LG, where L is a depth of flow. Okay. Next comes to Euler's number, ratio of inertial force by pressure force, rho AV square by PA. So V square by P, I'm taking rho at the bottom. So I'll have finally V by root of P by rho. Weber force, it's a ratio of root of inertial force by surface tension. Remember, Weber's number is mainly defined for your thin films and droplets. Okay, your surface tension is always defined for a droplet. So here what I'm doing, I'm taking rho L square. Area I'm substituting as L square into V square by rho sigma L My 1L will get cancelled. I'm taking rho down. So I'll have V square, square root of V square by sigma by rho L. So if I take the square root, V by root of sigma by rho L. Now here L is mostly your diameter, okay? Your length means your diameter. Your max number, last is your max number. So here it is your inertial force by your elastic force, square root of inertial force by elastic force. So rho A V square divided by Ka, A will get cancelled. I'm taking rho down. So if I simplify it, I'll be getting V divided by root of K by rho. Your root of K by rho is C, where C is the velocity of sound in the fluid. So these are the different dimensionless numbers. So in tomorrow's class, we'll be doing your models for all these. Okay. So we end the class today. Thank you.